All right. Welcome back to the final session of what has been a really engaging and interesting day of talks. So to kick off the final session, we have Sadra Jazayeri from Imperial College to tell us about bispectrum islands.
Thanks a lot. So let me begin by thanking the organizers for giving me the opportunity. So this is going to be about the work that was released during summer in collaboration with Claudia Deram and Andrew Turi at Imperial. So I was under the impression that I have 25 plus 5, but now I'm 5 minutes short. So I'm gonna do something dangerous, which is skipping part of the introduction. But I'm covered by some introduction that Chandra already gave. So I think that's fine. And for the rest of it, maybe I wait for the salvation by the organizers. Okay, so I wanted to tell you about how the bootstrap story started from 60s for amplitudes, but okay, so we don't have time for that. So let's jump to cosmology. So for cosmology, as inspired by the successes of the amplitude program in the past several decades, so the question that we want to ask ourselves is that how the initial condition of our universe is constrained by these fundamental principles of analyticity, unitarity, and symmetries. So this is really the inspiration, the main idea. But then practically, to be very concrete, so what I mean by this statement is that I want to assume that some period like inflation happened in the early universe. The universe underwent an accelerated phase of expansion, a fraction of a second after the Big Bang. And then the universe started a hot Big Bang phase. So then there was a thermal phase, and then structures, CMB was released, and then the structure was formed, and so on and so forth. So the usual story. Now the concrete question regarding this idea we want to ask ourselves is that what kind of correlation functions at the end of inflation are consistent? So in other words, if I have a healthy unitary causal time evolution during inflation, what kind of correlation functions can be imprinted at the end of inflation? And these in turn can be extracted in principle from observations of the CMB from the correlation functions of temperature anisotropies or density contrast in large scale structure. So at a practical level, so this such putative bootstrap ideology will be both conceptually and pragmatically very useful, because we should recall that thanks to the imagination power of humankind, in the literature, we have many models of inflation. However, on the other hand, we have only a limited number of observables or correlation functions that really, even futuristically, will be ever be able to measure. And this is like the 2-point function, 3-point function, if you are exceptionally lucky, the 4-point function. So, and the other aspect is that even extracting the detailed prediction of each one of these models for these correlation functions is a very demanding task. So you are dealing with the quantum field theory on a time-dependent background, as Chandra was explaining. So you are computing in correlation functions as opposed to in-out correlation functions. So these are by nature more complicated objects. So you might as well just give up on like doing this excruciating journey from the theories to the observables, and just look at the observables and see that like how the fundamental principles constrain these observables. So what sort of amplitudes and shape dependence of these correlation functions are actually have a chance of being realized in nature based on fundamental principles that we understand about quantum field theory and about gravity. So this is not completely new. There has been already some few hundred works in this direction in the community, but this has been mostly focused on perturbative aspects of this question, as also Chandra alluded to. On the non-perturbative side, there has been a much smaller amount of literature on the subject, and it is quite recent that we have started understanding, at least for fixed de Sitter background and without gravity. And that is, to be honest, very almost for any practical purposes, it is the best approximation, because gravity is just such a decoupled force during inflation that its corrections to correlation functions are almost never going to be detected anyway. So it is fine to decouple gravity. Now for quantum field theories on a fixed de Sitter background, so there are some interesting results. So for instance, people know how to decompose the 4-point function on the boundary of the de Sitter space. Okay, so in the de Sitter, you don't have you don't have all the tools that you have in your disposal in CFTs, but there is this partial wave conformal decomposition of the 4-point function. So the difference to the CFT is that now here, instead of having a discrete sum over delta, you should carry a full function of delta. It's related to the fact that you are only allowed to use the unitary representations in the bulk of the zeta because the theory on the boundary is not unitary. And that kind of poses some challenges. So for instance, we don't have a, for now, and as far as I know, I was hoping that Peter was here and Peter Krupchuk, and I could ask him what is the state of the art, because I know that he's working on this problem. But so for now, it seems that we don't have yet a full efficient numerical bootstrap, implementing crossing symmetry and positivity of the partial wave coefficients to get the full bounds. So this program seems to have been halted for now. And also for practical applications to real world, there is a concern. So if you rely too much on fixed zeta, then usually the correlation functions that you get are not interesting from the phenomenological point of view. So the amplitude is going to be very small, maybe a small proportional to the slow roll corrections. So for real world computation, and even for slow roll models, I would say that you have to break the zeta isometry at some point, because just the fact that you have a time-dependent scalar field in the background, it gives you preferred frame, so that the zeta boost at least are broken. So there are questions that how far we can get with non-perturbatively. However, we don't have to be that high-minded as far as observation is concerned, because if you look at the CMB map, you see that it is extremely close to being Gaussian. So I mean, we are not dealing with some sort of a strongly coupled correlation functions. So I mean, these are like almost Gaussian with the small non-Gaussianity that are probably going to be observed maybe in the next 100 years, but they are small. Therefore, whatever the underlying, maybe I should keep an eye on time. Whatever the underlying physics of inflation is, it has to be weakly coupled. So at least at the scale of Hubble. So this doesn't rule out having other sectors during inflation which could be strongly coupled. I mean, there could be some strongly coupled QFTs parallel to the inflationary sector, and these guys might be talking to each other. But however they are talking to each other should be described by some sort of weak coupling. Otherwise, you will see big non-Gaussianity in the sky, and you don't see it. So this suggests some simpler setup for your bootstrap if you want to still with some bootstrap flavor, but heavily relying on perturbation theory. And that is the following. So you can actually split. It is well defined now that you know that physics is deeply coupled. It is probably well defined to consider an inflaton sector at the scale of Hubble, which is weakly interacting. So you can write an effective field theory for your single field inflation, for instance, or multiple field inflation. But then you can also consider some other sectors in your the zeta, which might be strongly coupled. But then you can systematically couple these two sectors together, and then use the principles like unitarity, the zeta isometries, which might be approximate isometries, locality, to say something about these sectors and then translate those information into bounds on observables. But in order to go from this information to correlators, you can use perturbation theory. That's fine, because you don't need, so in other words, I don't need a full non-perturbative formulation of correlators on the boundary. That is almost never needed for real world applications. Okay, so with this, let me just make this idea more concrete by saying that, so I will consider a setup. So I will discuss a baby version of these nice ideas, which are the following. So first of all, for inflation, I just limit myself to a class of models that are called slow roll models of inflation. So basically, you have a potential almost flat, and then the inflaton is rolling slowly on this potential, and then the background is almost at the zeta because of the positive cosmological constant of this potential. So in a so-called decoupling limit, which I will be interested in, you send the M Planck to infinity and the H dot, the variation of the Hubble, to 0 in such a way that this product is fixed, which is proportional to the velocity of the inflaton field. So this, if you want, is something like the axion decay constant in terms of the fluctuations during inflation. So this, if you fix this fixed, then basically the problem simplifies. You can think of the background as exact zeta, and you can think of the inflaton field as an exact shift symmetric scalar living on an exact zeta. So the EFT that you write down is, so you can actually consider this potential to be constant. There is a kinetic term, and then there is a host of higher derivative operators suppressed by some scale. So this will be your influence sector. And this is like the only thing that you can write down. As I said, so here there are some assumptions about the fact that you are close to the slow phase, meaning that this kinetic term, this Lorentz-Merrill kinetic term, is the dominant in this expansion. There are models that go beyond this, and they are fine, but this will be the assumption. And then usually we consider fluctuations, right? So the scalar fluctuations during inflation around this time-dependent background. So these source the scalar perturbations that we see in the sky. So they are characterized by something, a dimensionless field called curvature perturbation. So this is like a number which depends on the position space, or usually go to momentum space. In momentum space, k, the 2-point function, is almost like 1 over k cubed. This is the famous scaling variance. And its amplitude is tiny, so it is around 10 to the minus 9. So this is according to the CMB observations. Now, going beyond 2-point function, so this was only the 2-point function. Going beyond 2-point function, there is the dynamical information and needs you to go beyond 2-point function. And the 2-point function for this, for instance, the first non-trivial non-Gaussian signal is in the 3-point function. So the 3-point function, the first operator that gives you that is a quartic interaction in this EFT. So this quartic interaction, in order to get a 3-point function from this quartic interaction, you need to evaluate one leg on the background as you expand around your wave, and then you get an effective Lorentz violating contact term. And from this contact term, you compute this Feynman graph, right? So you have a one vertex. As Sadra was explaining, you do an integration over time, and then you get a 3-point function on the boundary, which we call, and we love in cosmology, as the bispectrum. So this is like the holy grail of cosmologists who has been working in the trenches in the past few decades to observe or to make predictions about this bispectrum. Nothing so far has come to fruition yet, but hopefully we should keep an open mind. So this is the bispectrum, and what is interesting about this already from this very simple thinking in terms of EFTs, you can actually apply already the flat space positivity bounds for this coefficients. You might ask, we are in curved space, so how come you're assuming that C is positive according to Nima and friends in 2006? Or maybe the less credited paper several years before that this C is positive, so we are not in flat space. But the point is that the cutoff of this theory, for some detailed reasons that I can tell you, has to be actually much greater than Hubble. Therefore, there is a regime where you can go to the flat space limit, and then you have amplitudes, and you can assume that C is positive, no problem. And if you assume that C is positive, then it turns out that the bispectrum has to be negative. In fact, for any values of the momentum configuration K1, K2, K3. This is very interesting. This is something that you can rule out. You can go, and the sign of the bispectrum is something physical. So being positive or negative, you cannot kind of redefine it again away. So it is something physical you can check. So, and the shape of the bispectrum in this case, because you are truncating your EFT expansion at a particular level, let's say the first derivative nullified to the 4, then the shape is actually fixed. You can usually draw the shape as a function of the momentum ratio. So this 3-point function is characterized by, I have 5 minutes, right? Or 5 minutes, yes. It is characterized by this triangle. You can draw it as a function of this momentum ratio, and then it peaks at the equilateral. That's why it is called equilateral template. And usually it is normalized at the equilateral configuration as well. So it goes to 1. So the question is that how much of these results change? So far I was considering single field inflation. Now I want to consider other sectors during inflation, as I said, so with some richer spectrum. So there might be some resonances corresponding to Kaluza-Klein excitations during inflation. There might be some strongly coupled sector, as I said, for instance, the CFD operator. It is fine to assume that there are CFDs living inside the CTER, and they interact with your infloton field. So what are their exchange signature in primordial non-Gaussianity? That is a very well-defined question, and we want to answer that. And then can I still say, without knowing much about the UV competition, if I kind of integrate over the space of possible UV competitions, can I say something general about the bispectrum sign and shape? And the answer is yes. So the way to go forward to make progress is, as I said, you can start coupling your hidden sector through some composite operators. So these composite operators, you don't have to tell me what they are in terms of the fundamental fields in your hidden sector. You can just consider them as generic. So for simplicity, I assume a scalar operator. So the leading order interaction that you can write between the scalar hidden sector and the shift symmetric infloton field is this dimension 5. Well, we should be careful not to call it dimension 5 because this O could be a composite operator, but the leading term is this. And then using the two-point function of this operator, you can compute non-Gaussianity. And the two-point function, it depends on your UV completion. And the specific model that gives you this operator O. However, you can just use this KLM on the composition. I'm going very fast now, sorry. So there are just simple assumptions that I make about this hidden sector. I assume that it comes from a unitary sector. It is the Sitter invariant to leading order in a slower. That should be a good assumption. And also I assume that it is gapped for some technical reasons that you can ask me. So I consider that it's a spectrum doesn't have light fields, light scalar, so it only has principal series fields. And with these assumptions, the two-point function is completely fixed up to some spectral density function. So this is very similar from QFT course or maybe advanced QFT course of two-point function that they decompose into the two-point function of free fields. And this spectral density has to be positive required by unitarity. So if you now shove this inside your in formulation, you can draw diagrams like this. So this is a diagram for the three-point function due to the exchange of this operator O. Now all I need is to be agnostic about this spectral density and just use the spectral decomposition in order to find. So here now this is on the left-hand side, I have the Fourier transformation of the propagators, the in propagator or the ball-to-ball propagators of the operator O. So using this spectral decomposition, I can write them in terms of free propagators. Now this gives me a formula. It tells me that the exchange of the operator O, the result can be written as a linear function, as a linear superposition of the three-point functions induced by the exchange of fundamental scalars, just the simple three-level exchanges. So the non-trivial physics is in the spectral density. So whatever the model that you're considering is here, and it is positive. But we don't want to specify what it is. So we just want to be open-minded about it. And then these templates are very complicated, so you cannot write. So for amplitude, this is like only one line. But for cosmology, thanks to cosmological bootstrap, we have analytical results for this, but they are like a couple of pages long. So I'm not writing them down. But if you plot them in momentum space, they look like this. So in the squeeze limit, there are some oscillations. So these are called cosmological collider oscillations associated with particle production. Close to the equilateral limit, they look like analytic functions. So they look like what EFT would predict if you were to integrate out this intermediate particle. Okay, so going to the positivity, the question is that using this dispersion relation that I wrote down for the two-point function, can I say something generic about the bispectrum? The answer is yes. For instance, about the sign of the bispectrum, we proved that in this numerical interval, where so K3 divided by K1 equals 2 corresponds to the flattened configuration. And then there's a lower bound, which we found it numerically. So if you are in this bound, then we prove that the bispectrum has to be negative. This is just one example of the applications of some dispersion relations like this, that you can prove generic bounds without knowing what the spectral density is. And this is non-trivial. If you tomorrow find the bispectrum and in this range, and the bispectrum turns out to be positive, then it means that some of our assumptions is broken, and you learn a lot because you didn't rely on what the spectral density is in order to drive this bound. And also more than that, slightly more complicated and interesting, we computed like the shape of the bispectrum, again, normalized at the equilateral configuration. And here it is more complicated, but nevertheless, we proved that at a fixed configuration, if you fix your triangle, you can show that this ratio is bounded from both from below and above. So for this, we resorted to something like semi-definite programming, but maybe a baby version of that, because in this case, you have just a linear programming theorem, so you can set the denominator to -1 without loss of generality, and then the problem becomes linear in the spectral density. And then you have to just find the maximum and minimum values of your shape function. So we put bounds, so we have some islands like this, or maybe this picture is nicer. So you have the shape of non-Gaussianity, and whatever your theory is, as long as it is consistent, the curve that it predicts for the exchange diagram should be within this island. For instance, we consider as a non-trivial example the CFT, the exchange of CFT operators. So a scalar CFT operator, the two-point function is fixed completely by scaling dimension. And then we computed the exchange process. And we confirmed that the curves, even though they are different by varying delta, they lie in this window. Although the range of delta has to be limited in this window for some technical reasons that I'm happy to discuss. Future directions. So in the interest of time, maybe I just say, well, maybe I should double down on this 4-point function in the Sitter non-perturbatively. I think that's a very interesting direction if some of you want to, especially at King's with Peter. It would be very interesting to make progress in this direction. Now, also for our case, which was more perturbative, considering spinning operators, I only consider the exchange of scalars. But of course, if you want something like to cover like Kaluza-Klein excitations, you at least have to consider spin 1 and spin 2 exchanges in order to be a bit more broad. So thanks a lot for your attention.
Questions?
Thanks for a nice talk. Just a question, can you consider maybe some in-out quantity to use dispersion relation instead of using in-in?
Yeah, that's I see the smile in your face. I don't know if you're working, but yes, yeah. I think
No, I'm not.
yeah. No, we haven't thought about this, but there was papers by Scott Melville and Guy Pimentel, so they have considered. So the problem with the defining S matrix is like the lack of conservation of energy in the Sitter and also the presence of particle production. So your vacuum is not as stable in a sense, so it's a bit difficult. But maybe for some masses, like massive fields, you can kind of subtract the particle production and then look at what like the real interaction or contributions to particle production is. Yeah, it seems it seems to me
about the operator representation of S and T, right? The fact that they are not scalars.
Yeah, so there are several issues. I mean, to be honest, I haven't read those papers in detail, but maybe we can discuss. But it would be nice to consider at least some approximate versions of S matrix, maybe deep inside the horizon at the short distances, and that include the corrections from curvature perturbatively in powers of Hubble. Maybe that already teaches us something. I think in ADS that is kind of something similar that people do in when they start like writing down dispersion relations for your CFT on the boundary, and then you take the flat space limit, so you get the positivity for amplitude, and then you get like Hubble corrections. Maybe perturbatively in Hubble that one can do something like that, but yeah, but precisely how to do it, I don't know. So yeah, I think that is an interesting question.
More questions? Is there like a smoking gun for strongly coupled CFTs interacting with or there isn't?
Yes, yeah, for these particular scalar CFTs that at least we looked at, and they were also analytically solved by Guy and friends. So the shape of bispectrum that you get turns out to be very close to equilateral, as you see here. So the shape is kind of not dramatically different from the self-interactions of the inflaton field. So it is not clear to me. So at least if you look at like CMB observations, maybe it is hard to distinguish, but maybe if you go to galaxy observations and you can look at the squeeze limit, then in the squeeze limit, you see that like the scalings are very different compared to the, like if you have self-interactions, it goes as like A3 cube. If you have the exchange of a light operator, then the scaling changes. Maybe you can then look at the signatures of how the scaling dependence of the non-Gaussianity. So that could be a smoking gun inference. But I'm not sure if that would be completely different from the exchange of like just a light field. Yeah, it might be hard to distinguish them. Yeah, but it's interesting to see for yeah, smoking gun inference. Or look at some other observables, maybe as higher speeds.
Yes,
might be more interesting.